So friends, now we'll try to understand voltage, or more specifically voltage drop in a circuit, in an electric circuit in which current is flowing. How does voltage drop from its higher potential point to the last point, that is the lowest potential point, or conventionally we assign them positive and negative pole of a battery or the source. So let's assume we have a circuit in which we have a voltage or a source of EMF, and we have a resistance, and the current flows from positive, the conventional current flows from positive to negative poles in this direction, of course through this resistance. Now before we understand the voltage drop in this circuit, we need to clear some conventions or some concepts which will make it easy for us to understand how does this voltage drop in this circuit. So number one is, we always assume that these wires do not bear any resistance and there is no potential drop or there is no energy consumed. From this point to this point, the only part of the circuit which will give you the energy consumption or which will oppose the current to flow through it is this resistor only, or this resistance only. So in a way we can say that these wires are just diagrammatic extension of these two poles to make it clear that how this source is attached to some equipment or to some resistance, or how does the current flow. So we assume, unless it is specified in a condition or in a situation, we always assume that these wires are not going to consume any electrical energy and they have resistance equal to. Second very important concept that needs clarification here is that by definition we say that the rate of flow of charge is the time rate of change of flow of charge is going to be the current that is passing through this circuit. Now if we say some charge flows from this place to this place and maybe some charge is flowing further, but this is not coming at this point, or it is not coming at this point, or it is not coming finally back to this negative pole, that is the last point in this circuit. So but the charge has flowed. If you see here, you will have flow of charge. If you see here, you will have flow of charge. But if you see here, there is no flow of charge. If you see here, there is no flow of charge, because we are assuming a situation in which some charge has flown from this positive pole, but it has not completed the whole circuit. So here we need to clarify, or we need to understand this thing, that whenever we say that the rate of flow of charge, which means the number of charge flowing per unit time, we consider that the charge that has flown from this positive point, it has come across all the components of the circuit and it has come back to the negative or the lowest potential point in the circuit. That charge we are going to consider when we calculate the current or the charge. More specifically, we should say that it is not rate of flow of charge, actually it is the rate of flow of charge that flows from the highest potential of the positive point of the source and completes or traverses the circuit and comes back to the lowest potential or the negative pole of the source. This is going to be the charge which we are going to consider, and the amount of time it takes will give you the current in this circuit. Because if we have an open circuit and some current flows from this place to this place, we may say that the charge has flown from this part to this part, but it has not completed and it has not come back to the source at the other pole. So we will not say that this is constituting any current. So we will see that the charge that leaves this pole, traverses the complete circuit and comes to the other pole, then only we say that the charge is flowing, and that much of charge will be considered or will be accounted for in calculation of the current. Another important thing we must understand at this point of time is that the amount of charge that is going to flow through this circuit. So we can, for simplicity, we can state that the amount of charge that will leave this pole will be such that the total charge that is leaving this pole will have sufficient energy from this positive. You know that this is the higher energy, higher electrical potential energy pole. So you will have a value of V here. Let's say we have a value of 100 units here. and we have, let's say, millions of charges that are available, millions of electrons that are available at this pole, all the electrons will not leave this pole, because there may be a situation all the electrons will not be able to complete this path and come back to this place, because there is an energy that is required to come from this point, traverse this whole route and come to this point. So how much charge should leave this positive pole? Very simple. The charge which if given 100 unit of energy or 100 volts of energy or 100 units of electrical potential energy, it should suffice the amount of charge which is leaving this pole, and it should come back to the other pole. So in a way we can say that only those amount of charge carriers would flow from the positive pole, which in any situation will be able to complete this route within this energy. That is a limitation of the circuit, because the energy is given by the source only, and if the energy is 100 units, and let's say we have a situation in which only 2 units are required for one charge carrier, so 50 charge carriers would now move, because more than that cannot. You may have thousands of charge carriers here, but the energy is 100 unit, and 2 unit is required by each electron to move from this place, give some energy at this resistance also, and to come back at the other pole of the source. So if one electron needs 2 unit of energy, only 50 charge or 50 electrons would move, because that is the amount of energy that is available at this pole. So what decides the current, or what decides the amount of charge that will be leaving this place and that will be completing this, are 2 factors. One is what is the total amount of energy available with this circuit, that is the source, and second is how much is the energy that is required to complete this path. So if this is going to be more, let's say from 2 now it is 4, so the charge carrier will be 25, because now only 25 charge carriers will be spending 100 units of energy that is available. If I make it 1, so if the energy required to complete this circuit is 1 unit, 100 electrons will travel. So this is one thing, that if you change the energy consumption of this circuit, it is going to affect the charge carrier. You may do the other thing also. If I make it 200, now 200 units of energy are available, automatically everything will become twice, because now the double of the energy is available. So in this case 100 electrons will be available now, in this case 50 electrons, and in this case 200 electrons will move from this positive pole. So we need to understand this thing, that the amount of charge that will leave the positive pole will be equivalent to the sufficient energy that is required for all those charge to move from one part to the other part of the source, consuming all the energy that is required to complete this circuit or the. So let us understand an analogy which will further make it clear that how the potential drop occurs in a circuit, and how the resistance is going to decide that how much charge would flow in a circuit if the voltage is fixed for such a circuit. Let's say we have a highway which is of 1000 kilometers. So I have made 3 different cases that will be explaining one by one. So we have a highway which is around 1000 kilometers, and we have a lot of lorries which are waiting here to get fuel so that they can complete this distance. Now if it is a uniform road, by convention we have taken that the amount of fuel taken is 10 units for a lorry to complete this path from this part to this part. And the rule here would be that the similar as we have in the electrical circuit, number is that the lorries that are fueled here should be so that all lorries start this point and come to this end point. So there should not be a situation they are given less fuel and they are stopping midway. So the first rule is that they should be given enough fuel that they start from this point and they end this point. So which means in this condition they all should get 10 units of fuel, because that is required to complete this distance. The second rule would be that the lorries should not get more fuel than that also, which means even the 9 unit is not acceptable, 11 unit is also not acceptable, because the more and more lorries need to get from this point to this point. So if they have 1 unit here, it is a kind of wastage of energy, because it is not utilized for any other lorry. So each lorry will be so filled that it can just complete this path or this distance. So now suppose we have a tank, or we have a situation of a fuel tank where you have 1000 units of fuel. Now with this 1000 units of fuel and 10 units required to complete this roadway, 100 lorries can be filled, and 100 lorries will start from this point and 100 lorries will reach at this point, and you will say that the number of lorries is 100. Now take another case. In this case, this road was almost similar. At any point of time, we would say that the road is almost similar, speed is constant, speed is uniform, and the fuel, the 10 units of fuel was consumed in a very uniform manner. If you say half, 5 units were consumed. If you say quarter, 2.5 units were consumed. And if you say the complete distance, 10 unit was consumed by each lorry. Now here you see, take another case in which we have a very bad patch of water body on this highway. And it so happens that 10 unit of fuel is required to cover these yellow lines, which is a normal roadway. And 10 unit is itself consumed by this very small patch of road, which is very bad, and we say that the total is now 20. So now in this case again, many lorries are standing. We have again 1000 units of fuel tank capacity. Lorries are available in number, but the limitation is that now our rule number 1 was each lorry should get the fuel such that it should complete its distance, which means now in this case each lorry should get 20 units of fuel, because that is a minimum requirement, because now we have a bad patch of road in between. So in this case, if we see that only 50 lorries will start from this place, they will be fueled with 20 units of fuel, and each of them would be able to complete this distance, and we will find 50 lorries here. So now you can see that as you increase the resistance or kind of opposition, or as the road gets bad, the number of lorries are converted from 100 to 50. The fuel consumption remains same, which means the energy consumption remains same. The fuel was available same, but only 50 lorries could be fueled because each lorry was taking 20. And the condition is, the rule is, neither 19 nor 21 would be given to this situation, because if we give 21, we will not be able to complete 50 lorries. We will be short of some lorries because of some more fuel unnecessarily given to the lorries. So this is another case in which we have one patch of, we would say, high resistance or some kind of high opposition to the movement of the lorries. This is almost similar to resistance that we find in a conducting wire or a conductor. Now we take another case. We make it more complicated. So now in this case, we have two bad patches. One patch is of a very bad water body that is there in the roadway, and when we have a very bad pothole patch in which we have very bad potholes, and now the situation is 10 units of fuel is required to complete the distance, that is yellow line, that is a normal road. 20 is the unit of fuel that is required to clear this pothole porch, and further 20 unit of fuel will be wasted or is required to cross this water body, which means now to complete this point, start point to end point length or the roadway, we need 50 units. Here it was 20, here it was 10. So you can see now here it was 10 units fuel for the whole length, here it was 20 units fuel for the whole length, but that was not even evenly required. 10 was required for the majority of length, 10 was required for a very small patch, but because the patch was very bad, so it consumed a lot of fuel here. Here also the situation is a very long part of the roadway will still be covered in this 10 unit of fuel, and very small two patches will be covered with this extremely high amount of fuel, that is 20 unit and 20 unit, but eventually you will find that the total fuel required is 50. And now when we have 50 the requirement, only 20 lorries will be able to get fuel, because the rule is the amount of fuel required will be given to each lorry, not less than that and not more than that will be given. And the amount of fuel is here also 1000, here also 1000. So if this 1000 liter is a fixed, which is a kind of fixed battery or fixed source voltage, if the voltage is fixed, the number of charge carriers, because the charge need energy to come from one point to the last point. They cannot sit midway. So if you have very good road, you will have more charge moving. If we have slightly bad road, we will have lesser charge moving. And if we have a very bad road, we will have even lesser charge moving. But the condition is all the charges that start from this point will definitely come to this point. And when they come at this point, they won't have any energy practically. They will be almost at the potential of the other point of the source, which means if this is your source and these are the two poles, so when the charge comes back to this pole, it is almost equipotential to this point of the source. So they have to consume this complete energy. When they are here, they cannot hold any energy. So if they are filled with 50 liters or 50 units, or if they are filled with 20 units, or if they are filled with 10 units, this whole unit of fuel will be consumed in this roadway distance, and nothing is going to get accumulated here when they reach. So lorries are completely unfilled here also, unfilled here also. They have taken the fuel, they have consumed the fuel, and they have come back to the end point. So now when we know that electrons or the charges, in the conventional current, we assume that positive charges are coming, so we take this direction. So if we say that some charge carrier is moving from this point and all the way it is consuming some energy. So if there is no resistance, there is no special patch of resistance like this or like this, throughout this path, the energy will be consumed in a very uniform manner. So if they start, let's say, with 10 units, and if we divide this whole path into 10 parts, we can say that each and every part has taken 1 unit of fuel, because we assume that there is no special patch of resistance, and throughout this we will have 1 point of fuel consumed, and this is known as potential drop, because this is the energy drop. Here they started with some higher energy. At every 1/10 they lost some energy, and they carried it further with the leftover energy, and finally when they came back to the other pole of the source, they were left with no energy, and this 10 units of energy is consumed in this 10 equal paths if the resistance is uniform throughout this path. Now in this case, when we say that this is 10, and throughout this 10, so then we will say that it will lose a lot of energy, and it will lose suddenly 10 here. It will lose 1, 1, 1, 1, 1, 1, 1, 10, 1, 1, so that the complete is 20. So they started with 20 units of energy. They will lose 10 part of energy, 10 unit of energy suddenly at a very bad patch of road or at a very resistive area, and the rest of the energy will be again equally distributed or dropped equally throughout the path. You will see in this diagram that the lorry will start from this position, and because it is a constant speed normal road with no special patch of resistance or bad road, so throughout the length we would say that continuously energy in a very uniform fashion or in a very uniform way consumed. So at any point of time we can calculate the distance, and accordingly we can convert it into the fuel used. But here you would see that if we see the complete distance, and if we try to now find out that how much will be the energy drop or fuel consumed at any point, we will be making a mistake, because 10 fuel points or 10 units of fuel is just wasted in a very small patch. So now if we are talking about this patch, the energy consumption is going to be different, and if we are talking about this patch, the energy consumption is going to be different, because these two are of different resistance or different speed. For the lorry, different speed patches. So this patch is slightly better and this patch is very bad. So in such a situation, we need to specify that what is the resistance of this patch. Same is here. Here you have two patches, so we will have again a circuit, but this time we will have a circuit with two, and we say that it is R1, R2, rest remains similar. Now here again 20 units are wasted here, 20 units are wasted here, and 10 unit is consumed in this normal roadway, which means if we do a overall calculation, we have consumed 50 units, and this is consumed in 1000 kilometers. So we have a different fuel consumption. That is the overall. But if we say what is the fuel consumption of this part covering this part and let's say this part. So this is going to be very different, because here 20 units of fuel are wasted in a very small page. In the length it was similar, but it was very bad in the quality, and in the same length for a normal road we'll have, let's say, only 2 units of fuel wasted or 2 units of fuel consumed. So we can see that if the road condition is different and you have some special patches of different quality, we are going to have different energy or different fuel consumption for different paths. However, nevertheless, we can always say that as a charge carrier starts from one point, because that is the definition of the electric current, that the charge would move from higher potential to lower potential. So by definition itself, it means that as it starts moving, it will lose its potential, or it will lose its potential energy, or you will say that the voltage drops, because this is the difference of the two electrical potential energies, that is the voltage. So here it has some voltage, or here it has some electrical potential energy. Now that energy is reduced as it moves, depending upon the path, either the energy will drop or the voltage will drop uniformly, or it will drop at some point, at some part of the circuit uniformly, at some part of the circuits non-uniformly. So that is something different, and overall loss of the voltage would be the voltage that is applied or that is supplied by the source to this. Now let's say we have a situation in which, I repeat the case one first. We have a normal roadway and the lorry starts here with 10 units of fuel, because 10 units is required, and the lorry completes this distance. Now I put a bad patch here and I say that this is of 20 units of fuel consumption. So here the lorry will be filled with 30 units of fuel, and it will move up till this point. Let's say it has consumed 8 units, because 10 was the overall. Here it has consumed now 20 units, and it is left with 2 units which will be used in the last part of the distance. If I make it even bad, let's say if I say that this is 100 now, so the lorry will take 110 fuel, because 10 will be used for this normal roadway, 100 will be used for this bad patch. So you can see now how much is the ratio between the fuel consumption of this bad patch and this complete road. So previously it was just 8 versus 20. Now it is 8 versus 100. We can make it even higher. Let's make it 1000. So that is now 1000. So the overall fuel that is taken will be 1010, because 10 is the unit of fuel we are taking for this normal road. So 1010 is now the new fuel requirement for this lorry from the start point. And you see the total amount of fuel that is filled for this lorry, you see the ratio or the portion that will be consumed at this part is becoming higher. If we take a circuit in which we have a resistance, and now we know that for this normal wire there will be energy drop, that is, let's say that is E1, and there will be energy drop, that is E2, and this total energy drop is equal to the potential difference, that is the voltage. So as we increase this resistance, the more and more voltage will drop at this point, the more and more energy will drop at this point, because this remains almost constant, and the energy which is required to complete this circuit will be drawn from this voltage, as in this case. If more energy is required, less lorries will be filled, but each lorry will have more and more of fuel. Here it was having 10 units of fuel, here it was having 20 units of fuel, and here it was having 50 units of fuel. So you say that if the patches become more and more bad, each lorry will carry more fuel. Here also, if resistance is increased of the circuit, each charge carrier will take or will draw more and more energy from this positive pole, and in turn, because the energy remains constant for this constant voltage circuit, the number of charge carrier will be lesser. So the current will be lesser, but the energy that will be carried by each and every electron or charge carrier will be more and more. Now in such a situation, if they start with more energy, the energy which is consumed here is going to be higher and higher as we increase the resistance of this resistor. Now let us make it more interesting. Suppose someone wants to understand how much is the capacity of this tank. How much is the capacity of this tank? Now, someone is here, let's say someone is standing here in between, in midway, and they want to understand how much is the capacity of this tank. So, you know that lorries are filled, they are going here. The person does not have access to the fueling area, but they want to understand what is the capacity of this fueling area and how much is the fuel capacity of this fueling tank. So, what they will do, if it is a normal situation, each lorry would have 10 units and a lot of lorries will come and they will waste some potential energy or the fuel here, and rest will be measured here. But in this situation, you would find that they come with a higher fuel. At this point of time, if they start with a 50 units of fuel, because that is a requirement of the complete carriageway, 50 units is a requirement, but at this point 50 units is not consumed. So if you catch hold this lorry here, you will find that, let's say it has 45 units still left, because 5 are only consumed and 45 are to be consumed in the path that is to be followed. But you have catch hold, that guy has catch hold, the lorry is here and it has measured. So you can say that now he would know that, okay, at least 45 is the capacity of this tank. He would make it even more difficult. Let's say we have 1000 of the capacity here. So he would make this whole bad patch of road of 999 units of fuel. So now the fuel man will just give 1000 fuel to one lorry, because he understands that in 1 unit he would be covered, the lorry would be covering the normal road, and 999 would be required for this bad area, very bad area. This is the situation, this is the bad area. So 1 unit is required for this normal route and 999 is required for this very bad area. So the lorry starts from here with 1000 units of the fuel. Now practically it doesn't crosses this area. The lorry doesn't crosses this. Before it crosses this area, this man who was interested in understanding the capacity of this tank would catch hold this lorry here, and assuming that because 1 was the only requirement for the normal road and normal road is covered only, the bad road is yet to be covered, and there is some normal road left later also, which means practically 1 unit was required for this normal road. Most likely, let's say 0.5 units are consumed, and 999.5 will be the measurement of the fuel that is still available in this lorry. So, and this is almost equivalent to what it got filled. So this is an indirect way of measuring that what is the capacity of the fueling tank. So you make the resistance so high that the charge number, because had it been more than, let's say, 15-20 lorries, it was very difficult then for the person to measure each lorry, and then there will be measurement error also. So first of all, he tried to reduce the number to the minimum. That means the number from 10, the 100 or 20 or 50, he reduced this down to only 1 lorry. So to catch hold 1 lorry and to measure it for 1 lorry only, it was very practical and comfortable for him. And he made the resistance so high, because the rule was the fuel man would not give fuel until it is required to complete the distance. So if he wants only 1 lorry to travel to this distance, if he wants only 1 lorry to be fueled in any other situation, the only way is you have to tell the fuel man that the fuel required is 1000 liters, because the fuel man obeys only 2 rules. One is he would not give fuel more than required, he would not give fuel less than required. So if you want complete fuel to be given to 1 lorry, you would make a situation in which the fuel man should find that the complete fuel is required only for 1 lorry. So he will give all the fuel to the single lorry. And now the job is easy, because before this bad patch comes, you catch hold the lorry and you measure the fuel, and practically you have measured at a distant fueling tank's capacity by measuring the fuel available in this lorry. So this is something very interesting, and this is an application of the potential drop across a resistor. Same principle applies to this circuit also. Suppose we do not know the voltage of this circuit, or the potential energy, or the potential difference of the two poles of this source voltage. Now what we will do, we will make this resistance very high. We will make this resistance very high. So high that very less amount of charge carrier would cross this area. And each charge carrier which is crossing this area will be catched here before it enters into this bad area, because this is a very high resistance area. And you know that by that analogy, that the amount of energy which is wasted or which is consumed in traveling this wire is very less. So if we have a voltmeter, or if we have a system by which we measure the potential difference between this point and now any point, let's say this point, or let's say this point, that is the lowest potential, and the potential point before the resistance, we will practically find that this is almost equivalent to the energy which is available with this battery, because no loss or very negligible loss of energy has occurred yet, and most of the energy is still available. Based upon this analogy and the potential drop that we have understood along a circuit under influence of a voltage source or a source of potential energy, now we are in a position to understand and explain the concept of voltage divider. For a recap, let us again understand what happens in voltage drop in a circuit. With the same analogy, we have a fuel reservoir, we have a distance, and in distance we have a patch of bad road. This is to be covered by certain lorries, and the rule is the lorries that start from here should finish the end point, and there should not be any position in which the lorries are stopping midways or they are reaching the end point with some fuel left. So the rule for the fuel man is that the lorries are provided with the fuel that is actually and exactly required to match the requirement of the fuel consumption to cover this roadway. So we have now different examples, or we have different cases that we have assumed. Let us say in first case, 1 unit is the fuel that will be used in the road, which is normal. 0.7 is the unit of fuel which is before this bad patch. This is the bad patch which will take 9 unit of fuel, and later 0.3 unit of fuel will be taken, and this is how the summarize can be covered. 10 unit is the fuel required to complete this roadway. If we take a separate case, in that case we have again 1 unit, because the road remains same. If we need 1 unit to complete the road that is normal, and 49 units of fluid is required to cover this bad patch of road. So this makes the total of 50. Now if the total is 50, 20 lorries can be transferred from this point to this point, considering each lorry would take 50 units of the fuel. We can take an even worse example. The road remains same, so that is 1 only. So 1 unit of the fuel is required to cover the part of the road, and a very bad patch of road needs 999 unit of the fuel. So in this case, you can understand 1000 unit is required only for a single lorry. So only a single lorry will travel from this point to this point. And if you see that the maximum fuel consumption is going to happen in this bad patch of road. So if we are here just before this bad patch, if there is a man who measures the fuel available with this lorry, you will find that the fuel available is going to be 999.3 units of fuel, because only 0.7 unit of the fuel is being consumed in this road coverage, and this is almost equivalent to the fuel with which the lorry has started, which in turn is almost equivalent to the capacity of the fuel end or the tank from which this fuel is being given. So in a way, we have tried to measure the capacity of fuel tank by restricting the number of lorries to 1, and before this bad patch, which was a limiting factor before this bad patch, before this patch of bad road, where it was actually going to consume a lot of fuel. We have measured the fuel, and this is an indirect method to measure what is the capacity of this fuel or this source fuel tank. If we take the same analogy into an electrical circuit, we have a circuit which has a potential difference of 100 volt. This pole is at 0 volt and this pole is at 100 volt. And again we assume that if a charge tries to move from this direction and traverses this complete path and come back to this pole, it is going to consume 0.25 unit of energy before this resistance. In this resistance it will have different values depending on the resistors, and after this it is again taking 0.25 unit of energy to come back to this pole or the negative or the other end of the supply source. So this 0.25 and this 0.25 are constant, so this remains 0.5 if you add both of these values. And now when I take different examples, suppose we take a resistance which consumes 9.5 units of electrical energy. So the total electrical energy would be 10 units, and the number of units available are 100. So in that case 100 will be the 10 will be the I, because one charge is taking 10 units and we have 100 units available, so we will have only 10 charges which will be corresponding to 10 units of currents. Now if we further increase the resistance and if we make it 19.5, which means the total would be 20, because 0.5 is being consumed in these wires and 19.5 will be the potential drop across this resistance. So in this case total would be 20 units, and if 20 units are to be consumed or are to be utilized by the one electron or one charge carrier from positive pole to negative pole, we will be having 5 charges that can move under such situation, because the total is 100 units available with us. Now we take an even higher example and we say that 99.5 is the potential drop or the energy consumed or the energy required to cross this resistance for a charge carrier, and we know that 0.5 is a constant energy requirement to cover these part of the circuit. So this makes it 100, 99.5, 0.5. This is for the resistance part and this is for the rest of the circuit. So this makes 100 unit or 100 volts requirement of energy to travel one electron or one charge carrier from one part of the circuit or from one pole of the source to the other pole. So practically it means that only one electron or correspondingly one current, one value of the current will be able to flow only. You can see as we increase the resistance, the current is dropping down because the voltage is constant, this energy is constant. And you can also see that the maximum potential drop or the maximum energy consumption or the maximum energy utilization is happening at the resistor if it is taking more and more and more value. And the percentage of the energy with which the electron or the proton or the charge carrier starts on this point increases for this as the value of R increases. Here you can see that the percentage will be lesser because this is 0.5, this is 9.5. Here you can see this is same, but this part is increasing. Here also this part is same, but this part is many-fold increasing. So you can see that in this part, the total energy with which the charge carrier has started, maximum or almost practically all part of that energy is being used or consumed across this resistor only. Now we are going to apply this thing in a very interesting manner to measure an unknown source of voltage. Here, for the explanation and for the simplicity of the example, we assume that there is a potential difference of 100 volts available at this source, and this is how we explained all these equations to make this example. So now recall that at the initial start of this discussion, I mentioned that these wires are practically having no resistance. Rather, they are the part of the source, and we can say that these are the extension of the poles. Just for the simplicity to make diagram, we have made like this. This is actually your source. This complete is your source. the components that are now enclosed by this figure are your source, and this is actually the component which is known as a resistor or some component which is consuming the energy. Now, because any source would have some resistance until it is applied to a resistor that is external to the source, so that resistance is the part of the source, we say. And since the purpose of a source or the purpose of a voltage generator is to generate voltage, but now because of practical situations we can assume or we can explain that there will be some resistance definitely inside this source also until the actual potential difference reaches to the resistor or to some external component. So that part we say is the internal resistance of the source. So we say that there is some internal resistance of the source or voltage generator. We can represent R1 as the internal resistance of some source that is supplying the source voltage or source electrical potential energy, and because this is the inherent resistance, so we denote it like this in the circuit. And now we assume that anywhere in the circuit other than this resistor, which is an external component, anywhere in the circuit whatever is the resistance, we have denoted it with this symbol and this R1 value. So R1 is going to be the internal resistance of the voltage generator. Now, as this voltage generator is consuming some part of its energy or some part of its voltage due to its internal resistance, so such a voltage generator is practically known as non-ideal voltage generator, because it is generating a voltage which is slightly lesser than its capacity, because a part of its voltage is consumed by its internal circuitry or internal component or internal conduction of the current, and by the time it reaches out so that it can be applied to some external component, some part is consumed. So we say that this is a non-ideal voltage generator. So this is a non-ideal voltage generator with R1 its internal resistance, and now it is connected to an external resistance that is R2. Now with this analogy that we have just drawn, assume that we do not know the voltage or the potential difference across this source. This source can be battery, this source can be any biopotential, this source can be any muscle, this source can be skin, it can be any, it is a source which has got some potential difference across its two ends. And now we want to see what is the potential difference across its two ends. We know now that there will be a current that will flow from all these sides, and the current is like the charge carriers depending upon the resistance offered by this external component and resistance offered by this internal component, because that is going to be the total energy requirement of this path, the current would flow. So the current would be higher or lower depending upon the value of R1 plus R2. So now we understand that this is going to be the value of the current depending upon the resistance R1 and R2. And if we draw the parallel between the analogies that we have previously done, where we had a resistor and we had a source, or we had this kind of arrangement where we had lorries and we had a roadway and we had a fuel requirement, if we make this R2 very high, then practically a very less amount of energy will be wasted up till these 2 points, because practically a very less amount of energy. Again, in this example or in this case, we knew that practically only 0.7 unit of fuel was wasted and 999.3 was available before this very bad patch of road, which was going to consume the majority of the part of the energy with which this lorry started. Same way, if we have a charge carrier here and we know that this R1 is very less than R2, we say that R2 is very high than R1. So in such case, whatever energy with which this charge carrier is starting, it will have practically almost same energy across this R2, and it is going to consume, or it is going to give that potential drop of maximum of its energy across or in passing this R2 if we only measure the potential difference between these 2 points, we will find that this is some value which is almost equivalent to V, because the current started with some value the charge carrier started with some energy, a very less amount of energy is consumed up till this point, and the rest of the energy is available, and this is almost equivalent to this source voltage or source potential energy. So friends, let us apply this principle of voltage divider into the context of biopotentials. Assume that this is a source of some potential, that is biopotential. This can be some muscle, or this can be some tissue which has some potential difference, and this potential difference traverses some path and it comes to the skin. So let's say this is underneath and this is the skin surface. Now some of the energy of this potential difference is wasted while reaching from the depth to the skin. And you know, the source of skin impedance are, number one, the resistance, the ohmic part, the material through which the current is flowing will definitely have some opposition, and that is the ohmic part, which is due to the electrolytic conduction, and the other part is the capacitive reactance part. So because of these two, we have a complete tissue impedance, and the more the frequency of this biopotential, less is going to be the capacitive reactance. So there will be a variability, because depending upon the range of the biopotential frequency, this value will vary. So the R1 is not going to be constant, because R1 is constituted by two parts. One is the ohmic part or the material part that will remain almost similar. So we can say that ohmic part is similar, but this capacitive part is highly variable, because the biopotentials may vary in their frequency from some value to some larger or very lower value. So this is your internal resistance of the source potential. We can assume that R1 is the source potential's internal resistance. Now applying the same analogy, we say that if we want to measure this potential difference, make this value very large than R1, because you know the amount of charges and the energy the charges take from this potential will be consumed in this complete circuit, and the higher the amount of R2, more will be the energy consumed across R2 only, and very less portion of the energy will be consumed in rest of the circuit, that we have already understood. So based upon the same principle, we say that if R2 is very high, let's say 100 to 1000 times high than R1, so in such a case, practically at these 2 points we get the voltage almost equivalent to the voltage of the biopotential or the source potential. So this is a method by which we can measure the potential differences that are at deep and that they come at the skin after some skin resistance or impedance, and if we apply a measuring device and if we fit in a measuring device across these 2 points such that the resistance of that measuring device is very high, in the tune of 100 to 1000 times than the internal resistance of the tissue impedance. So now we understand that if we want to measure the potential difference of this biopotential, which is created or which is generated by some deeper tissue, and it comes to the skin, and in this path it comes across the tissue impedance, which is sum of ohmic resistance and the capacitive reactance that it faces across its path. Now after this, when it comes at these 2 points, that is the skin surface, if we apply a measuring device and if we make the resistance of that measuring device very high than that of the internal resistance of this biopotential generator, we take it in the tune of 100 to 1000 times high, the resistance or the internal resistance of the measuring device is going to be 100 to 1000 times higher than the internal resistance of the biopotential or the tissue impedance. So practically we say that at these 2 points we will be having the potential difference which is almost equivalent to the potential difference of this biopotential, and this is an indirect method to measure the potential difference of a biopotential generator, which is it is found that the tissue resistance is in the order of 10 kilo ohms to 1 mega ohm. So this is generally found out that the tissue impedance, the overall impedance, is in the range of 10 kilo ohm to 1 mega ohm. And now we know that we have to keep the resistance of the measuring device at a very high value. So we keep normally from 1000 mega ohms to 10,000 mega ohms the resistance of this measuring device, which is put across these 2 points, such that it will be so high that we can assume that the energy that is consumed up till skin is so low that it can be almost equivalent to the energy that is available at this potential difference of the biopotential generator. So now we know what is a voltage divider or a potential divider. Basically, it is an arrangement of resistors, and each and every resistor is the patch or a part of the circuit which has very high resistance. And these are the areas where majority of the energy is consumed or majority of the potential drops takes place. So if we want to divide this potential into different values, so based upon some calculations, we can set in different resistors such that if we take the potential between this and this, it will be the highest potential because the charge has not traversed any resistance. It is picked from here only and it is picked here. So it will have some resistance. Now if we have output between this point and this point, you know the charge has traversed both the resistors, so the potential drop will be more. So friends, now we know what is a voltage divider or a potential divider. It is basically arrangement of resistors such that the potential with which, the potential energy with which a charge carrier is starting from one pole of the source will be divided into different potential drops across different resistors. So if we have one resistor smaller than the other resistor, here the potential drop is going to be lesser, and here the potential drop is going to be very, very high because of energy required to cross this resistor because of high opposition or high resistance will be very, very high. So this is basically an arrangement in which the potential difference with which a charge carrier or current start can be dropped in a set value depending upon the value of this resistors, 1, 2, or we may have more resistors. The more the value of the resistor, more will be the potential to cross across it, and less the value of the resistor, less will be the potential difference or potential drop across it. So depending upon our need, we can choose. Now here we wanted very less of potential drop at R1, so we made R2 so high that practically no energy is lost, and we are assuming or we are taking that the potential that is picked by our measuring device at skin surface is almost equivalent to the potential difference that is generated by this biopotential generator or some tissue. So friends, now we know that based upon the principle of voltage divider, we can have an arrangement in which by putting a measurement device to measure the voltage across 2 points of skin, we can indirectly measure the biopotential or potential difference that is generated at the deeper site. The only thing we need to consider is that we will see that what is the range or what is the order of the tissue impedance, and we will make our device internal resistance 100 to 1000 times more than that of the internal tissue impedance. So practically the range is the tissue impedance are in the order of 10 kilo ohm to 1 mega ohm, and normally the measurement device will have the internal resistance from 1000 mega ohm to 10,000 mega ohm, and we can measure the biopotential.